All right. So we're gonna go over some stuff with this architecture I'm working on. I don't know if I reworked this on the last video I did or not, but let me close this door actually. Um, yeah. Okay. So I simplified it down to 16 instructions so it can all fit within a four byte opcode because previously I had it as a let's go back to this version. It was a variable by opcode before, so some of the instructions would have four, some would have five, and that would be based on the 15th bit. So that's basically 24 instructions because you can fit 16 here plus eight with obviously one in the front as your most significant bit, but we're not gonna worry about that right now. And I extended the register. Since I was able to make it four, I could also make um the register values like one bit bigger. So they're now 16 accessible registers in each category. But the only thing is I have a 4-bit immediate because I wasn't really sure how to fit a whole immediate. And my solution to that was to add an instruction called load H, which would load the highest 12 bytes of R1 with a value. So in theory, like let's say you wanted to fill or load a really high value, you can either load it into memory when you program the device, or you can load the highest 12 bits and then add the last four. So that should give you access to all 16 16 bits in some manner. And then I also added some more branch instructions. So you jump, which is just an unconditional jump. Branch if equals zero. This is if R1 is equal to zero. Branch if not equal to zero, if R1 is not equal to zero, and then I had to put a out instruction in as well. So this would just cause it to send data out to a peripheral, which I have to work on too. But that'll probably be the last thing that gets worked on. Um, I mean, I'll get the signals going, but I don't know if I'll actually have a controller just yet to handle all those signals. It'll be the last thing I work on for sure. Um, and then we have halt, which just halts the CPU. I'm not really sure. It might be more like a no op rather than a halt. Um, that might just be a mistake on my part, or oversight, because I'm not really. I don't know if there's a point in doing halt. I might just do a no op, and then when it reaches the end of memory, it just stops. Or keeps going, I guess, until yeah. Um. So, or yeah, we could just do jump infinity. Yeah, that's fine. That works. Um, okay, so let's talk a little bit about the signals, the control signals. Okay, so this is my iPad here. So we have our little program counter, our instruction. How this works is you obviously have your fetch, exit, decode, and execute. Um, but what we have here is we have our ROM, which has um, all of our code basically. So that gets programmed onto the chip statically at the beginning of FPGA at the beginning. Um, I could have made like I have two memories in here, just a ROM and then a um, like general memory. It doesn't really matter what's where really. Um, I could have just connected this to this and added a few more elements within the circuit to allow for you to use the first, I don't know, X bits of this are just reserved for code, and then anything after is like whatever data you want to address. And that could be a compiler thing. It's not a big deal, but for this, I decided to go with ROM. Depending on how much space this takes, I might have to change how that works, or buy a bigger FPGA. I'm currently using the RD A7 or S7. Well, actually, should I real quick? Yeah, the S7. I know the A7 is a little better. Um, but it's the RD S7 25, not the 50. So it is a little bit smaller. We'll see if that makes a huge impact on our final product. But yeah, I mean, let's just start with how an add instruction would look like within the uh circuit. And by the way, this is just to kind of like figure out more so what my circuit is doing and not show it off. So I probably do have some things I will change as I'm going through this. I can already think of a few off the top of my head. But yeah, let's get into it. So an add, I'm gonna assume that our instruction register has been loaded with our instruction, which is 0000. That's the opcode, and then 12 bytes. To make this simpler, I'm just gonna write the decimal values for each. So say add into our target, which is 1. We're gonna add 2, register 2, and register 3. So what that's gonna look like is it goes to the instruction decoder, gets decoded, gets into the control signal generation matrix. That might be jargon, but this is just like a control unit to generate signals. I don't know what the word matrix is in there for. I remember seeing it somewhere and I was like, oh, that's cool. But yeah, so that's gonna generate all the signals. I think the only signal that doesn't generate, here, let me just pull up my code, is the immediate, no, that does. Uh, it might just be the is ALU operation value. And I think I might just pass that over into the control unit as well. Mm, yeah, I think I will just pass that over into the control unit as well. Um, just to make it simpler. So we can just draw a little line. So we have from our instruction decoder, we have our instruction data, which is just the that's the input, and then our outputs are the opcode or register X, register Y, register Z. Our ALU op, um, which would just be the I'll show you this other screen real quick, which would just be these 3 bits, sorry. Because how I configured it is that 0 through 7 are all or 0 through 8, I guess, are all ALU ops. Yeah, I think I have to update all of this, but yeah, 0 through 8. Um, so if it starts with a 0, it's an ALU up. If it doesn't, it's not an ALU up, and that's just how the code ends up looking. Um, so yeah, we'll just pass those over um on the iPad side. So that's from here to here. We have our all that value, all those values going in, and then our control signal generation matrix. We'll just call them control signal generation generator. Has to generate a few signals. So it's gonna do this. Um, it's gonna have an immediate enable, which is gonna be set to 0. Our immediate value is gonna be don't care because it doesn't matter, or maybe it's gonna be tri-stated. But it doesn't matter what that is. Um, and then our mux. There's actually this is our mux for now, I guess. But it basically just says if immediate enable is enabled, don't put Y on the bus, the Y output on the bus, put the immediate on the bus instead, which gets moved around. Um, so then we have 1 going into Z, 2 going to, wait, no, 1 going into Z, 2 going into X, and 3 going into Y. Our read write enable is going to be high. Our jump unit our jump unit is going to be off, so it's going to be 0 there. Our ALU, I'm realizing I forgot some things. So I believe this is a 3-bit ALU dot, we'll call it type of operation. So in this case, what's getting passed into the ALU is 000, because that just gets forwarded from basically the instruction decoder into the ALU. And that's I believe that's a hardwire connection that is going to be made. And then we have let's just open up the ALU real quick. Yeah, so we have ALU add, which is if our ALU add is 000, then we're just gonna add 1, 2, and then put it on the result bus. And the result bus is going to connect to Z. So this is our ALU.enable. I just realized I didn't put that on the screen. Yeah, sorry. So we have our ALU over here. If we have ALU add, which is 000, it's going to be in1 plus in2 that gets put on the bus. Yeah, moving on. So we're going to have an ALU enable, which is the important signal that's going to be generated. Immediate enable is going to be an important signal that's generated. Read write enable is going to be an important signal that's generated. Our memory enable is going to be 0. Important read write enable doesn't really matter because enable is off, but that would be a 0. And that's just what add. Add 1, 2, 3. I haven't finalized the notation for this. That's something I'm going to figure out later, but it can be like add like that, similar to MIPS, or like add R1, R2, R3. Doesn't really matter. So that's an add. Let's do a add I, and we'll keep the things the same. We'll do R1, R2. Let's switch up the last one actually. R4. So we're gonna have 1 put on Z, 2 put on X, and 4 put on Y. No, this is add I, so it doesn't matter what's there. So we're gonna put a 4-bit immediate. Let's call it. That's a maximum value of 15, unless we want. I believe I'm gonna do signed. Signed add I. So that's technically that's -8 or -728. Let's just put 3 on there for now. Okay. So we have 3. So our immediate enable is going to be high. Read write enable is going to be high. Immediate value is going to be 3. Jump is going to be 0. ALU. Make this 3 bytes. Maybe I'll have to add this in a second. ALU enable is going to be on. Our 3 bytes are going to be 0, 0, 1. Functionally, 001 and 000 look the same to the ALU, so it does not really matter what gets put on that bus because it still is an addition operator. It gets two 16-bit numbers, but this 3 actually does get sign extended within the I believe the MUX does sign extend the other 8, no, the other 12 bytes, high 12 bytes of the immediate. So that just gets pulled down, put onto bus, and goes into Z. So that gets stored back into 1. Let's do the next one, which is gonna be Let's skip a few. I'm gonna go ahead and skip all the ALU operations because they're all very similar to this. Imagine this. Add I is the only exception because it's just the only operation with an immediate. Ooh, I guess shift has an immediate. Um, Fuck it, let's do shift. So shift has a sign immediate, so we'll do R2, R6, and we're shifting it -2. So what's gonna happen there is immediate's gonna be turned high. Read enable is gonna be turned high. Immediate value is gonna be -2. It's gonna get put into this bus. I might have this flipped one way, but -2 gets pulled over here. The value in R6 gets put down here. We have 0, 1, 1, 1, or well, I guess just 1, 1, 1 getting put onto this bus here because this is 3 bytes. ALU enable is obviously on. This is gonna be 0. I don't know if I'm gonna include. We'll talk about that later. It's fine. Jump is gonna be 0. And that's just gonna open the bus and then put back in. Then we have let's do load word. That's an interesting one. So load word is a RT. So we have, say we have R3 and then R6. So we have our address that we want to load from in memory into R3 and R6. So Z gets set to 0, but read write enable is 0, so it doesn't really matter. You know, read write enable is this is 3. This is 1. X goes to 6. Y goes to 0. Or I guess Y gets tri-stated. In this scenario, yeah, Y would just get this set to 0, and whatever value is in Y will get pulled over to the in memory. So initially the way I had it working was you'd have memory store enable and memory load enable, and these would get set depending on whether you're trying to store or load. In this scenario, just the IP that is available to me. We'll pull it up real quick. The IP that's available to me, memories and storage elements, Rams ARM block memory generator. Let's launch this real quick. We can see this. So just a single port RAM, which is what I want. Obviously I'd have to configure it, but this would be a 16-bit address. Clock would be our clock. But what's unique is that they have a DNA and DOUT-A. So my Y would just be connected to DNA and my Z would be connected to DOUT-A. So I wouldn't necessarily have to need these things because it would just kind of look more like this. Let me draw that up. Oh. It would just kind of look like this without any of this in the middle. We just have DN and then D out. And DN doesn't matter since we're doing a load operation. Whatever gets put on DN is not saved, but the address that we're requesting for D out, the address we're requesting gets put on D out, and that just goes back up the bus, and into Z. So our value for Y could be like, we could be looking at the 13th register, but it doesn't matter because whatever value is getting put on the bus does not go into memory. And our ALU enable is low. So this is getting tri-stated. So whatever value is getting put on the bus, basically like It just goes from memory into Z. It's not super complicated. Um, but I could either tri-state the bus and add ALU, the output of ALU onto there, or I could just throw a little mux in 2 to 1. We'd have 1 and then we'd have 2, cross out this, and then we'd just have a is ALU op the same so like we talked about earlier, available on here. So if it's an ALU op, it's obviously gonna be put on from ALU onto the bus. Otherwise, it's gonna be memory onto the bus, no matter what happens. Yeah. So that's load word. Store word is very similar. I would just turn read write enable would be 0 here actually, but our memory would be enabled. Um, our jump would be 0, obviously. Uh, immediate enable would be 0. Yeah, but we'll just put our y as an x for now, just as don't care. So now let's do, I mean, store word. We can do store word too. It's fine. We'll do R3, R6, 3, 6, X. Doesn't matter what's on Y again. Actually, no. No. This is the other way around. So it would be store word um store word to the address in R3, whatever is in R6. So in this case, actually, what would happen is 3 would be our input to address. So 3 would be over here. Is this right? I'm getting R3 written too. 3 would be our so we're loading the address, what the value of the address in R6 into R3. We're loading the value of R6 into the address at R3. So what I could do actually is for like load and store operations, I can just short these together. So the compiler would just put, I know in here I have it as zeros, but it would just be the same value of RS1 twice. So 3 would get put, or I get, yeah, 3 would get put onto that bus. But the only difference is with load word, our read write enable is high. With store word, our read write enable would be low here. These are combined for now. Or they're not combined. They just have the same value. So they would just be the value in R3. So that's going to be X. And then R6 is going to hold um, value, right? So we're going to need 6 on this bus. Ooh, I still feel something's amiss though. To the address. So we have on X, right? We're loading R3, R6. So we need let's assign values just so this is easier to think about. R3 is equal to 0, 0, 0. R6 is equal to call this 0x05. Well, let's make it decimal just so it's easier to understand. And we'll assume these are 16-bit decimals. 0, 1, 0, 1. So I need 0, 1, 0, 1 on this bus, and I need 3 on Z. Correct. Okay. So let's do the same thing here. R3 equals 0, 0. No, R3 is the target address. Or no, I guess for store word, we could do the value R3 is getting written into R6. or the value at R6. Yeah, let's try that. So we're trying to write, so we'll do R6. So in this one, let's write an equation. Just think. Um, so let's say R3 is equal to mem of R6. Yep. And here we'll say mem at R6, lowercase, is equal to R3. So we gotta flip it around the other way. So mem at R6. So on X we have to put the value of 6. So that was the value of 6 was 0, 0, 0, 1, 0, 1. It's gonna get put on this bus. And I need the value of R3 to get stored. So the value of R3, no, the value at R3 has to get put onto the bus. So Y would have to go to 3. Is that what we had earlier? Yep, that works. Cool. So R3 is equal to R6. In this case, R6 is equal to R3. Because 3 gets put on this bus, or the value at R3, which is R6 equals 0, 1, 0, 1. R3 equals 0, 0, 0, 0. So Y gets it to 0, 0, 0, 0. ALU is off. Immediate is off. Rewrite enable is off because 3 will also be getting put onto Z. Jump enable will be off. Read write enable will be 1. Memory enable will be 1. And we're obviously storing it. Perfect. Okay, cool. I'm glad we sorted that out. Um, Now we can do all the jumps. I think we'll do jumps and then that'll be it. But so we'll do jump. And then we have a 12-bit. Let me just try another screen just in case. We have a 12-bit target we can jump to. Um, so what would happen there is that 12 bits would be put onto this bus here. So let's say we'll call it instruction 5. We'd get 5 put onto this bus by this C control signal generator. Um, but our jump out would be dependent on, so our immediate value enables 0. Our X gets set to, actually, what a better way to do is we'll do branch equals and branch not equals. BEQC, we'll use 5 again. So what happens here is the control signal generation overrides whatever was um, put by the instruction decoder onto X, and we'll put 1 in there. And on Y, it doesn't matter. On Z, it doesn't matter. Immediate gets set to 0. This doesn't matter. ALU enable is 0. ALU type does not matter. I'm not even gonna write it actually. But our jump enable, what's important is our jump enable is set high. Our jump type is set to, I know all 3 of these had a jump type. There's a certain instruction. Let me pull it up. So BEQZ is 0, 0. So 0, 0 gets put onto jump type. And the value from R1, which is put on 16, gets pulled up into the jump unit. And the jump unit just evaluates if it's, since we're doing a equal to 0 jump, is this value 0? And if that value is 0, it puts out a 1. And that jump out just rewrites the program counter to whatever new value it's supposed to be. Um, yep, perfect. And if it's 0, it's just if this value is like, let's say 3, then our jump out is going to be 0. This is going to be 0, and that program counter is going to retain its value, and this value is just going to keep changing. Perfect. Okay. So that's how branch equals and branch not equals works. Branch not equals. Oh, I just realized I wasn't sharing my screen again. Oops. Yeah, sorry. Let me just talk through that again. So we obviously have our value of one that gets put on the bus. Our jump enabled is set to one. The value of one of R1 gets put. Let's say R1 is 0, gets put on this bus. Jump type is 0, 0. Jump out is 1. So jump out, that 1 would go up here, and it would allow us to rewrite our program counter. But let's say our value is a 3. It knows that the jump type is branch if equals. 3 is not equal to 0. It's going to output a 0 at jump out. So jump out is going to say 0, and program counter is going to be able to retain its value. And the same thing happens with branch not equals. And then we just have jump. So with jump, if our opcode is set to, I forget what the exact value was. It was jump no condition 1 1. So if 1 1 is put on the bus here, no matter what is put on X is always just going to be a 1 on jump out. So no matter what happens, that value on this bus 5 or whatever here will get pulled into the program counter, which will update for the next cycle of fetch. But yeah, perfect. So that was about everything I wanted to cover. Or actually, no, we can talk about the out instruction too. The out instruction is the same thing. I believe I'm gonna change it from what I currently have it as. I have it currently as a 12-bit like peripheral output thing. So you can put it on 12 peripherals, but I think what I'm gonna do instead is I changed it and I was thinking you have a 4-bit target peripheral, so you have 16 different peripherals you can put a value out to. And then you have your source register. So uh, you just kind of have whatever that. So you'd have, let's say, peripheral 5, and the source address is R3. I'm gonna take, I'm gonna put 3 on this bus. These don't matter. This is also we need connected to a peripheral unit, basically. P unit, we'll call it for now. Which is gonna have a P dot enable. So the control signal generation matrix is going to turn penable on to 1, and it's also going to put those 5, like this number 5. It's going to have a 4-bit target. So that gets put on that bus with a control signal generation matrix. Everything else here is going to be 0, zeros across the board. The enable is going to be 0, 0. So the only thing that will happen is that R3 gets put on that bus and gets sent up to the peripheral unit, and the peripheral unit just when it gets enabled, it just latches that value and puts it onto the peripheral, whatever that may be, an LED controller or like a 7-segment display. Um, but yep, and that's about it. And the no op is just gonna be zeros everywhere, so it's just gonna waste an entire cycle of um, fetch, decode, and execute. But yeah, that was about it. I just kind of want to talk about the generally how this would work. This also helps me like kind of think through my process, um, especially with the load word and store word. That was helpful because I wasn't able to I guess I thought about it, but I need to verify my thinking was correct. Um, but yeah, all right. I'm gonna go hop off and work on uh some of the code. Trying to finish this by oops, I just opened another thing of Vivado. It's fine. By the 6th of January. So we'll see what happens. All right, cool.